All right, hello and welcome. In this video, we're going to look at how to calculate this RC low pass filter. So in this case, we know it's a low pass filter because all high frequencies are going to be dropped across that capacitor to ground and all low frequencies are going to be stuck in the circuit. Right, so we have resistance across the top here that allows everything through. And then at this parallel node, anything that is allowed across that capacitor will go directly to ground and anything else will be left to go towards the output voltage. And so we know that this is going to be a low pass filter. So we want to go after our cutoff frequency, and that depends on our time constant. So our cutoff frequency, Fc, is equal to 1 over 2 pi. It says we're talking about a frequency, and then our circuit here has a resistor and a capacitor, so we'll use our RC time constant, which is just our resistor multiplied by our capacitor. So we have all those values, we can plug that directly in. So 1 over 2 pi multiplied by our resistor of 150, multiplied by 150, and then multiplied by our capacitor of a real small number there, 5.1 times 10 to the negative nano, which is 9. All right, so that's our frequency. We've got 208.045 is there also, and that's in hertz right now, but they want it in kilohertz, and so we'll move that decimal point from its previous location back here forward by 3, and we'll get 208 kilohertz. So that is our output frequency. We could type that in over here, 208. And after that, we want to go after our output voltage, and that is again our voltage divider equation, but this time our output voltage is across our capacitor. And so we need to put that on top. So in this case, the voltage divider equation uses a level of Ohm's law, so we just got to make sure that both of our components are in ohms. And so that means that we need to use our XC as what we want in our voltage divider equation. We'll divide that by what we have, which is basically our Z value. And then we'll multiply that whole thing by our voltage source, Vs. Right? So we need to figure out what most of these values are. We have voltage source, but other than that, we don't have anything else. And this is going to be our V out. Okay, so we'll start with our XC. We just found our frequency, so now we can apply our XC equation, 1 over 2 pi frequency times capacitance. We know all those values, so we'll do that, 1 over 2 pi. We'll multiply by our frequency of 208. No, we didn't multiply. Multiply by 208,000 for our full frequency value. And then we'll multiply that by our capacitor value of 5.1 times 10 to the negative nano is 9. That gives us 150 for our XC value. So our XC is 150 ohms. And we'll plug that in, but we don't have our Z value. Our Z value can be calculated out as the rectangular form. We can put that in here. We can say it's 150. Because we're working with a capacitor, it'll be a minus J, and then our XC value is 150. And so we can rotate that over into rectangular form. We don't care about the phase angle because we don't need a phase angle for our output right now. So we can send this out and just go after our magnitude, which is our square root equation. Square root of our first number, our resistor there, 150 squared, plus 150 for our XC squared. And that gets us a Z value of 212. And that's in ohms. And so now we have everything we need to plug into our V out equation. We have XC, which is 150. Say that up here, 150. And then our Z value on bottom is that 212. Those are both in ohms. And then our voltage source at the end here, we also have as 5 volts. So we'll plug that in. I'll set that into our calculator here. So 150 divided by 212, and then that whole thing multiplied by 5. 3.53, so we'll round it up, 3.54 volts. And that is what we expect our output voltage to be, 3.54. So let's check that. And there we go. So if you guys have any questions, feel free to reach out.